Just a minute. Let me record this one. Oh, just give me 1 minute. Record. Hmm. So bipolar junction transistor. Okay. So basically, it is a three-layer device. Now, first of all, why call it as a bipolar? Bipolar means you have two type of charge carriers. One is holes, one electron. Okay, and electrons are majority charge carriers in n-type section, and holes are the majority charge carriers are in the p-type sections. So because if I want to explain the operation of a transistor, I need both kind of charge carriers, minority as well as majority. Okay, so why we call it BJT, bipolar BJT, because both type of charge carriers, both type of charge carriers are required. Okay, now both type means minority as well as majority charge carriers, because both type of charge carriers are involved to its operation. We call it bipolar junction transistor. Now transistor word means what? Transistor, if I say transistor basically is made of transfer of resistance. Transfer of resistance. Okay. Now transfer resistance means the main use of transistor is for amplification. Okay. जैसे ही मैंने if I give some signal, okay, I want to amplify that signal. Okay, either in inverting or non-inverting configuration. So when I say if I want to amplify, that means my power voltage gain. I want voltage gain. Okay, either I want voltage gain, I want power gain. So transistor has a property if it is suitably biased. Okay, so if I want to amplify, I need to apply some suitable biasing, and once it is suitably biased, I can amplify any signal, apply to its input. Okay, so transistor main use is for amplification. And if I want to amplify signal, if I want to amplify a signal, what does it require? It require proper biasing. It require proper for amplifying signal, for amplify signal, transistor need to be biased. Okay, accordingly or properly, what are the requirements are there? I want to amplify signal, or if there is some other application, for each application there are different kind of biasing. Now biasing, you understand what is the meaning of biasing. I need to apply some voltage across some DC bias to the two junctions, because it's a three-layer device, it is a two junctions, so both these junction has to be biased. Okay, so now why we are able to amplify, because the resistance one part, if I go from input to output, one side is input, I will discuss what is input and output now, and other side is output. So input side resistance is very low. Okay, whenever I apply signal, it faces very small resistance. So small resistance, input side. While output side, where I'm obtaining the signal, where resistance is very high. high resistance, small resistance, high resistance. Okay. Now, once resistance become high, you know what is the voltage? Voltage is I into R. Okay. Now, if my input current and output current are almost same, there is a no change in input current, output current, then what will become? This side voltage will become high. Yes or no? Okay. If I say my output is say R0, I0. This is my output resistance. This is my output current, and this side my input voltage is I input, Ri input. Now, if somehow if I make I apply biasing in such a way that my I input is almost equal to I output, but my R naught is very high compared to the R input, then this V naught will be very high compared to the V input. Yes or no? Tell me.
Yes.
So if because V naught is one side is resistance is very high, other side resistance is low, but input currents are almost same. So that means I can amplify my signal. That is the basic principle behind the junction bipolar junction transistor. Okay, it is called transfer of resistance. That one side resistance is low, input side resistance is low, output side resistance is high, and some configuration current almost same. Current does not change, so we get the voltage gain. Voltage gain. If there is a voltage gain, there is a power gain. Okay, and similarly, if somehow if this is a one type of amplification, there is a possibility that I output is also high. Okay, this is a one configuration. If it is possible, you have a V input, I input, Ri input. Now other side you have V input, I output, R output. Now it is possible that I naught is also greater than I input, and R naught is also greater than Ri input. Then that case you have a more amplification. Okay, resistance is high, and the current is also output current is also very high, so that also amplification. Okay, and we may have a third case that resistance is current only. So now what is happening here? One case here, voltage is current is same, voltage is increasing. Here what is it is here current is also increasing, voltage is also increasing in output. Third possibility is as only current increases, voltage does not increases. Okay, that is also one kind of amplification. So that there are three way we can amplify the signal. There are three configuration. So before that we discuss how to operate and how to bias, because the first requirement is that you need to bias your transistor. Okay, so first we understand what is the structure and what is the meaning of biasing, and how we can amplify. That is the basic. Circuits of transistors are very easy to solve. Okay, only couple of things initially you have to understand, that why are you putting that values. Okay, and that rest thing is very easy. Just try to understand the fundamental behind the transistor. So first thing is construction. So it is a 3-layer device. It is a 3-layer device. Okay, so you have a transistor P and P. Okay, so this is the PNP transistor. You can you can also have a NPN transistor. N P N transistor. Okay, now PNP, one section is your ammeter. one section, this is the base. Mid thing is a base, and this cross section terminal is your collector. Okay, this is your emitter, this is your base, and this is your collector. Okay, now let us understand what is the characteristics of these three layer. Okay, emitter section, the doping of emitter section is very high. Okay, so if I say doping level, okay, so the doping of emitter is very high compared to the doping of base, and compared to the doping of collector. That means collector has the lowest doping, because at the collector I want to take the voltage. So less the doping, higher the resistance. So this section has a very high very less doping. These sections are conducting. So conducting means there will be low resistance. Here this section is high, so that the resistance is high, because I want output should be high resistance. So this section will have a very low resistivity. Okay, so doping level. Second thing, cross section area. Cross section area. Cross section area of collector is very high. Collector cross section is high compared to collector cross section area of your emitter, and its cross section area of this is your base. B for base. Okay, E for emitter, B for base, and C for collector. Okay, now the third thing is thickness. Okay, so thickness of base is very small, thickness of base is very small, say 5 micrometer. They can be 50 or 100 micrometer, but that is only base signal. So basically layers are there. There is one layer of say 100 micrometer of P type, then there is a base of say 5 micrometer, and then there is a emitter layer of say other 50 micrometer or 100 micrometer. So this is a basically 3-layer structure. Okay, for drawing construction I'm showing like this, but it is a layer structure. Okay, it's not like this, it's a layer structure, because this is not a ये इतना बड़ा बड़ा नहीं होता है. This is only micrometers thickness layer structure. Okay, so now this property is very important. The base thickness is very small. Okay, that makes some difference between a transistor and between two back-to-back connected diodes. Okay, so here we have two junctions. This is emitter section, this is a base junction, this is called EB junction, and this is called your CB junction. So there are only two junctions, EB junction, emitter base junction, and collector base junction. So you clearly understand what is the meaning. This is EB junction, collector base junction. So you have, this is EB junction, and you have a 2-second, you have a collector base junction. Now, instead of making like this, I can make a 2 diode P and then NP. This is looking like a this device. So why do I require a transistor? I can connect 2 transistor like this way. Okay, similarly I can make this like this. So why do I require a transistor if the same, if this both the geometries are same, both the it is also 2 junction, here 2 junction, but there is a major difference. Okay, here comes the design, the part of the design which makes this compared to this one, and this is different. Why? Because your base is very small. Okay, the thickness of base is small, and that design feature gives the capability that to the transistor that any input current without any loss can reach here, because it can very easily go. Very less negligible loss of current will be there. If a charge carriers are coming, they can directly go to here, and without any loss, and they can reach to here. So there will be almost current will be input current and output current almost will be same, which we require, okay, for our amplification. So that is the important feature between this and this one. They are not exactly, they will not function exactly same. This has a very small base width. That is a characteristics. Okay. Now I told you that if I want transistor to work, I have to apply proper biasing. Now, proper biasing means what? Proper biasing means we have two junctions. Okay. Now, two junctions can be biased in 4 ways. Okay. So I have EB junction. I have a CB junction. Okay. And this is my serial number. Number one, I can make it forward bias, and I can make it reverse bias. And now operation amplifier. For amplifier, one junction should be forward bias, other should be reverse bias, and it is required that your EB junction, ammeter based junction, will be always forward bias if you want to work as an amplifier. So that is mean biasing. This junction should be forward bias. Now forward bias, reverse bias, you understand na? If P is connected to the P is a forward bias, if N is connected to the plus of battery, it is a reverse bias. So this junction we have to make a reverse forward bias, and this junction we have to make a reverse bias here. Here I have to apply voltage such that this is connected to the positive and disconnected to the negative, that become reverse bias. This is connected to the positive, disconnect to the negative, this become forward bias. Okay. So if you make EB junction forward bias, CB junction reverse bias, you can amplify any signal. Okay, that is a biasing required for amplifier. There are other thing is what you can do. You can apply, say, I apply forward bias here and forward bias here. Both junction forward bias. In that case, it will work as a switch on. So when you apply forward bias, reverse bias, the operation region, okay, operation region is called active region. Okay, you write here active region. If both the junctions are forward bias, and this is used for active region, means the active region is used for amplification. The application is amplifier. Now, if both the forward bias, now then the transistor is set to work in the saturation region. Transistor has 3 regions. Depending on biasing, saturation region, and this is for switch on. Okay. And a third thing is both are reverse bias.
Cutoff region.
Cutoff region. This will be work as a cutoff region. That is switch off. So these two has a application as a switch, and this is application as an amplifier. This type of biasing is a application amplifier. And the last one is that is rarely used. This is reverse bias. This is forward bias. Okay. That means now this becoming forward bias, this becoming reverse bias. That is an inverse operation of this one. Okay, that we generally don't use, or very limited applications. So we won't discuss here. This is the inverse operation, inverse region. Inverse or active region become opposite. Okay. Now things become easy. You now first we'll discuss amplification, then we'll discuss switch on, switch off application. There's mainly two application of. Then circuit applications are many, but operation wise, there are two basic things we don't understand. Now this is the EB junction and this is CB junction. Okay. So let us understand now the working of this one. Shall I erase this one?
So please wait.
Yes, sir.
Okay.
Okay.
So now transistor can be operated in three configuration. Okay, three configuration you can use, because it has three terminals. But you have to make one terminal common, because we want to make input output only. We have to give input and we have to get output. So we require only we don't require three terminal. We have one terminal we have to make common, because we don't have four terminals, three terminals only. Two input for two output. So one terminal we will make common. So there are three combinations. One is called common base configuration. Common base configuration. Okay. In this configuration, current gain is, there is a no current gain. Current is almost a unity current gain. Okay. So no current gain. So unity. So current. So only it has a voltage gain. So this type of configuration has only voltage gain. Okay. And second is your common ammeter configuration. Okay, this has a both voltage gain and current gain. And we have to discuss all the things for common. We are going to our syllabus. We'll discuss mainly common ammeter configuration, because all the exams problems 99.99% comes on common ammeter configuration. Okay. And third is common collector configuration. Common collector configuration. Okay, that is rarely used. We don't require for our applications whatever syllabus says. Okay. Now let us discuss first what is common base. Common base we'll discuss a little bit. Our main focus will be on common ammeter. Okay. But just for starting, we'll start with a common base. So let us discuss common base first. So I'm erasing this one. So you have two transistors, NPN. Okay. Or so first we'll discuss say PNP only. Yeah. So PNP symbol means common base means you have this is symbol of transistor symbol. So if I want PNP, that means current is going from P to N. So this will be your base. This is your base. This is your collector, and this is your ammeter terminal. This is the symbol of transistor. Okay. For PNP, current always go to from P to N. Okay, conventional current direction. So we'll put a symbol here, PNP. Now, what do you mean by common base? So first we're discussing common base configuration, CB configuration. So here this base will be common. Here I apply, because this is a collector. Okay. If I want put, I can put a resistance, say RC here. And I am putting say a battery VCC, and here this should be forward bias. So here, if I want, I can put a resistance, say RB, which is ammeter. So R input you can say RC, RE or R input, you say no issue. Ammeter is connected, so RE also you can say. And other you can say here, you have a biasing, okay? Some biasing here. So I'm applying to the ammeter, so this is battery is VE, and this is applying to the collector, so I'll say this is the battery. Now P to P is forward bias, P to N minus this VCC, this is called reverse bias. So this is the general biasing. Okay, you require two biasing, EB junction and CB junction. EB junction should be always forward bias, CB junction should be always reverse bias. That you have to make sure. This junction should be always reverse bias. This diode or this part of the junction, PN and P should be minus and should be plus. P should be plus and should be minus. That is your this one. Now what I am going to do, I am going to change this voltage. This is a variable voltage. This is the variable voltage. Okay. Now I have to apply some values. Okay. So if I apply some here, what will happen? A current will flow in the circuit. This current is called ammeter current. This current is called ammeter current. Because here this junction is forward bias. So if any diode is forward bias, then what will happen? A diffusion current will flow. As I increase the voltage, the depletion layer width is a depletion layer width. The depletion layer width will decrease, and this diode will conduct, and you have a IV characteristics of this diode will be how? What is IV characteristics? It will be like this. So basically, the junction current is flowing. If the junction current is flowing IE, and you are applying voltage VE, what is the drop across the diode, which is called VBE, because VEB or VB. So here common is base, so VEB. Now you apply voltage drop here, VE. Generally we write it VBE, okay, VEB, and you keep on increasing voltage. But this voltage will, whether it will increase or it will increase, or it will be almost constant. Tell me, VB will increase or it will be almost constant?
Increase.
Huh? If I'm increasing this one, this VB will increase or not increase? How does it?
Definitely will increase.
Huh?
Increase.
Increase, sir.
Increase means how much? Suppose if I'm applying here 1 volt, there's some VB, 5 volts, some VB is there. So if you see the so some drop is here, there's a KVL, some drop is there, some drop is there, but this drop is always almost constant. You see this, na? This if you apply now, you have to apply some voltage to here, some keeping some voltage of VC here. This voltage is what? This voltage is this is VCB, which is negative voltage. Okay. Now if you apply some VCB, say VCB 1 volt, okay, and this side, and inside you are applying this one, so some current will flow. So you're applying some voltage, so now you're increasing this voltage, so current will increase. You see, you're increasing the voltage, this current will increase, but the voltage drop is almost constant. What is the value of this voltage for silicon?
0.7 volt.
Yeah, yes, that point you have to remember for transistor operation. That's your VB is almost constant. It will vary a little bit, 0.678. Okay, just for some variation will be there, but IB characteristics is like this only. So it will be almost constant. We can say almost constant. Now VCB is say 1 volt, and this is your VEB, and this value will be almost cutoff voltage. So this value is called, this curve is called input characteristic. This is your input characteristics. every transistor has a two characteristics, input and output, because we want to see which junction has a resistance low, which junction resistance high, because that is the operation, low resistance to high resistance. So we'll see here, this is the input characteristics. This is input characteristics in common base configuration. And what is input characteristics? IE versus VEB curve or VBE curve, keeping VCB constant, VCB constant. Okay, this kind of curve you make draw in your laboratory. Okay, if you have BSc laboratory or MSc laboratory, there is a practical called IV characteristics of transistor in different configuration, common base common. So what you do, you apply some voltage here, and now you change the voltage and you measure this current, IE. By making this one, this type of curve will come. This is called input characteristic. That is input current versus input voltage. Input current is emitter current, input voltage is VB. This curve is called input characteristics. Okay. Now what does happen if you change? Now what will happen? Here the majority junctions are holes. So here holes, you are applying battery terminal plus here. That means you are reducing the barrier width. So holes will diffuse here. So a current I will form. Okay. Now what will happen? Because this barrier is very small. The barrier will become small. Diffusion started. Now this base is very small. Okay. Now this hole here, you have a holes. Here you have a electrons, here again you have holes. So these holes, when you reduce the barrier, this hole start diffusing here, and here some electrons are present. Now some of this IE will recombine with this electron. So when they recombine with electron, some holes will be decreased, and now here you are applying a reverse bias NP, reverse bias. And reverse bias, what happened? Reverse bias happened due to the minority charge carriers. Now here, so these holes are coming, and these holes are directly injected in the P side. Here, negative battery. This battery will pull all the because this section is very small, and here very high voltage is there. Here in this section, very high electric field is there. Okay, high electric field from here to here. So holes will directly pushed away to here. And what will happen? A current will come here, which is called IC. And I is almost equal to IC. Now, what happens? Because some of the recombination happening here holes armies coming. Here holes are coming, holes are going here. Here some electrons are there. Some holes will recombine with their remaining. All the holes will pass here, and they will current IC. So because electrons are losing here, some electron will come from the battery, and opposite to the battery, a current will flow, that is called IB. So transistor is basically a current control device. Okay, and that is the main operation. Your I is almost equal to IB plus IC. Okay, is that point is clear to everyone? I am applying battery. Holes are pushed here. Some holes are lost here, but almost 98%, 99% holes reach here, and that holes are swept away by this battery. Okay. Now, if what happens if I increase this battery? Here I have put 1 volt. Now say I put 2 volts. So when I put 2 volts, I get a graph almost same voltage like this. VCB equals to 2 volt. Now you say, why does VB decreases slightly? That is not a very important concept, but we not use for exam point of view, but just for understanding, I am plotting this one. If you want to understand, otherwise not necessary. Now if I increase this VCE, my cutoff voltage will decrease. Now why does cutoff voltage decrease? This is my cutoff voltage. This, how much push I required electron to go from a hole to go from pass to this junction. Now when I increase the VCB, this is VCB. Here reverse bias is increasing, yes or no? This junction is reverse bias. This junction is NP, and I'm applying VCB here. I'm applying VCB N2 plus. So this junction is reverse bias. So when I apply increase this one, the depletion layer width will increase. Okay, depletion layer width has a function of, you have a N and you have a P, and now if I reverse bias, the depletion layer width will increase. So when depletion layer width increases, what will happen? This base become thinner, and now base become thinner, so you require less voltage to make it conduct. Earlier your base was this much. Okay, now if you reduce the base, now VEB only operating on the lesser part. Okay, because there's a depletion layer, so you require lesser voltage to push the electron. Okay, that's why this VEB value, it will come from 0.7 to 0.6. Okay, but we will always take it to 0.7. Okay, that's why it's not very useful concept for application, because we have to take always VB as a 0.7 volt whenever we'll solve the circuit. But you can understand, this is called base width modulation. Okay, what is the base width modulation? This small concept, base width modulation. What is called base width modulation? Increasing the reverse bias, increasing the reverse bias. Okay, increasing the reverse bias at CB junction decreases the base width. This is called base width modulation, and with base decreases, you require lesser voltage to penetrate the holes, or this bias means, you say if this biasing is increasing, this width is also decreasing. So this width is decreasing, and this junction width is decreasing. That means you require lesser VB. Okay, now this is your input characteristics. That is not much useful. The useful thing is your output characteristics. Okay, so before I discuss output characteristics, I want to emphasize there are 3 currents. Okay, now you see you have this junction NP. Okay, so this side IE current coming, this side IC current is flowing, IB current is going down. IB, this is all result of diffusion. Is there any one more current is there? Tell me, is there anything one more current is there except these 3 currents? Can anyone tell me? Is there any more current is there in this junction?
Is it displacement current, diffusion current, diffusion current?
So this is diffusion current. You're applying here voltage. Okay, barrier height decreases, current whole diffuse here. You swept by this battery. Okay, somehow lost, so they make a base current IC. Now this is here is a forward current, and these B and C are result of IE. What about this one? This junction. This junction
there
is
may be
reverse bias.
Drift
Reverse
current.
current.
Drift current.
Reverse current, reverse saturation current, because this is a diode. You are making this diode as a reverse bias, plus minus. So here also some current will flow, na? ICO, I naught, saturation current. Okay, we call it ICO because base is there. So common base I naught is the reverse saturation current. Okay, I naught is the reverse the reverse saturation. This current also flowing here. That is separate. This current is coming IE, and this current we because of this battery we are pulling this current, and this current is coming here, and this current forming. But here in this junction there is one more current which is going from here to here, down to up, and this current is called what? Reverse saturation current, ICBO, because it's a common base configuration. So I write I common base reverse saturation current. This is also flowing in. There are total four currents in the transistor. Okay. Now we have to write the relation between all these current. Okay. Let us write, and then we will discuss the common output characteristics, which is more important for us than the input characteristics. Okay. So I am putting more effort here because this one first class what you should know the basics, then things are very easy. Okay. Now let us say this is ICBO. Okay. Now write the equation. So IE, so your IC is combination of IE current coming, some fraction of IE goes to forms IE. So IC is made of IE, some fraction where alpha is almost equal to 1. Okay. Almost equal to 0 0.9, 0 0.8. Okay. You can say range. Generally in the question it is range is given 0 0.8 to alpha is 0 0.998 or 99, say. Almost equal to 1. So some fraction of IE forming IC plus ICBO also coming. ICBO also coming. Okay. This combined together forms IC. This section and this section combined together forms IC. IC involve ICBO also. Okay. Now what about IB? Okay. Now I have to write the I equation for IB. How does base current flows? So base current, alpha part of I is going IC. 1 minus alpha part of IE is due to make from IB plus ICBO going opposite way. So I have to put ICBO here. Is this equation are clear to everyone? Tell me.
Could you please repeat the IB?
So IB is alpha, 99% of IE forming going here. 1% of IE is coming here. 1 minus alpha. Because IB coming because of this one, this is a diffusion current, na? Because of this one also coming, and because of this one also oppositely going current. So this is alpha part is going here. 1 minus alpha part of I is forming IB. So IB. So this is the one. This is 1 minus alpha I coming here. Alpha I is going here. You can understand this alpha I going here plus ICBO, that is IC. Now 1 minus alpha E coming here, and this going ICBO is opposite, is going up. So this is the sections. So this is the current balance. KCL only. Alpha is going here, so 1 my alpha is going to here. Okay. Similarly, ICBO going down, so IAP here it is adding, and here in this side we have to decrease, and we have to subtract that one. Clear?
Yes, sir.
Now you add both these equations. So what you get? IC plus IB. What is? Tell me. If you add that one, what you will get? Sum of these.
IE.
IE. Understand?
Yes, sir.
This is the fundamental equations for transistor in common base. These are fundamental equations. What these three equations are called? Fundamental equations for transistor. Okay. Now, the second thing I want to discuss the common output characteristics, input characteristics, and output characteristics. Now, shall I erase this one?
Yes, sir.
Yes, sir.
Now, we have seen that my input characteristics means what? Input characteristics means input current in common base configuration. Input current is IE, input voltage is VEB or VBE, and this is 0.7. Okay, so this type of characteristic has a very low resistance. Low resistance. Why low resistance? If I calculate the resistance of this curve, that will be what? Delta VEB upon, if I say input resistance, RI upon
Delta IE.
delta IE. Now you see, this is less, this is more. Change in beta is more, this is less. So this RI is only a few ohms. This resistance is only a few ohms. Because current is, you apply little bit voltage, current is running exponentially. Okay. So this section has a very, if I plot say IV curve like this, IV, what is the resistance of this curve? Tell me. What is the resistance of this curve?
Zero.
Zero, sir.
Zero, very good. So this is also almost zero, less, because this is also like an exponential. If not like this, at least this is like this. So this type of curve shows less resistance. So that means input side has a very less resistance. Now we'll go back to the, so this shows zero resistance. Why zero resistance? Because the tan theta slope is 90.
Slope is zero.
So slope is 90 infinite. Okay. So if you want a delta, this Ri is, if I get a slope is infinite. Delta IVE, this IV is infinite, and the Ri will become opposite of this one. That will be zero. Okay, that will be zero. So just give me 1 minute. Now let us go back to the output characteristics. Now that is very important. You have to understand this one. Output characteristics means output current IC versus VCB. Now, what is output characteristics? Output characteristics is called curve between IC versus VCB, keeping input current IE constant, is called your output characteristics. Output characteristics. So plotting output characteristics, what I require, this should be forward bias. Some current is coming here, and now I am collecting that current using applying VCB. Okay. So say some current is flowing here, some IE is flowing here, and I know if I know IE, if I know the alpha, I know what is IC flowing in the circuit. So some IC is flowing now. Okay, some IC is flowing, and now what I'm doing, I am increasing VCB. So what will become? If I increase the VCB, some ICO will also form, and what will happen? Slowly, this current will increase, and if I plot the curve, this curve will go like this. It will become constant because this is your IC, this is your IE, constant current, and IC is almost equal to IE. So when keeping this current constant, when I'm plotting IV characteristics, I have to apply some voltage, so some IE will be flowing. I can measure that IV, and now without touching this battery, I will increase this battery. So all this current I will capture. So this shows this kind of graph. Okay. Now now I will further I will increase the IE. I will change the value of IE, and I'll further increase this one VCB. So I'll get different kind of characteristics like this. This is some value of this is some value of IC1, say some value of IC. This is IE, say IE is 1 milliampere, say IE is 1 milliampere. This IE, say 1 milliampere. IE is 2 milliampere. If I'm plotting 2 milliampere, IC will be almost 2 milliampere. Okay, almost slightly less than, but I'm keeping almost same. Yeah, IC will be also 1 milliampere. Now, if I change this one and again increase the voltage, this whole current will become here, and you get this kind of curve. I say 3 milliampere. IC will be almost 3 milliampere. Okay, VCB.
सर एक्सक्यूज मी सर सर ये आई की वोल्ट सर करंट सर के बढ़ाएंगे कैसे सर?
यहाँ इस बैटरी से
बैटरी बढ़ाएंगे ना सर बैटरी को?
हाँ बैटरी बढ़ाएंगे तो कैसे बढ़ेगा? ये बढ़ेगा ना आई, बट ये VB तो फिक्स रहेगा। ये देखा नहीं कर रहा, ये तो फिक्स है, ड्रॉप तो फिक्स है,
हाँ
पर करंट तो बढ़ रहा है ना।
हाँ सर,
जैसे
मतलब पहले वाले केस में सर इसको कांस्टेंट रखेंगे, इस वाले केस में
हाँ,
इसको
पहले में इसको कांस्टेंट रखेंगे, और हम क्या कर रहे थे, पहले वाले में इसको कांस्टेंट रखेंगे, इसको वेरी करेंगे तो ये करंट बढ़ेगा। ये तो इनपुट हो गया। ओके, अब इसमें क्या कर रहे हैं, इसमें इसको एक बार फिक्स कर देंगे। जैसे मैंने कुछ बढ़ाया तो ये तो फिक्स रहा, करंट मेरा ये आ गया। सेकंड टाइम मैंने करंट ये कर दिया, थर्ड टाइम मैंने करंट ये कर दिया, फिर इसको करंट को बढ़ाने के लिए इसको बढ़ाना पड़ेगा ना।
हाँ सर,
हाँ, so I have fixed this some current value. I can change the IE by varying this one, but this voltage will fixed, almost fixed. But current I can change by varying this one. So first time I have changed this one, I have fixed this is my IE, and now I'm changing this one without keeping this first. Second time again I'm changing this IE, and now in this curve again I'm changing this VCB, and I'm measuring this one. So I will get this type of curve. Now you have to tell me. You have to tell me what is this. This is like this, and then this is second time this one, third time this one, this curve this time. Okay. Now if I say if I go negative side, if I go VCB negative side, what will happen? Tell me. VCB, if I make it this is positive, this is negative. If I make it forward bias, this VCB is actually negative, but I am plotting positive side. If I go up, if I make it this forward bias, if I make this plus, this minus, this plus, this minus, then what will happen? Tell me. This IE will increase or decrease? Capturing will increase or decrease?
It will decrease.
Decrease. Well, holes are coming here, and I'm with minus, I'm pulling these holes. If I change this junction, if I make forward bias, that means I'm pushing back these holes. Are you getting? So if I make
Yes,
this
sir.
one, slowly this current will become zero. This current will become zero. This voltage is called early voltage. Early voltage. Now I'm not going to discuss these things because this require for engineers. We are which is going deep in these things. Okay, I did only amplification part. So this is my IV characteristics. So tell me now this junction has a 3 part. Now suppose I0, initially I0, then what will be the value of IC? Tell me. If
That
IP
is
is
also 0.
0, why? IC is equal to, tell me what? Alpha IE plus what?
I
Plus
ICBO.
ICBO. So even though this is 0, some current is flowing here, yes or no?
Yes, sir.
So if I 0, then also I get some IC value. This is I 0, but then also I get some value of IC, which is equal to ICBO. Okay, now this junction has three reasons. You tell me what are these reasons. In this section, in this below this section, tell me when I see I0, when I0, my EB junction is forward bias or reverse bias?
It will be reverse bias.
There is no voltage here, that's why no IE coming. When I is 0, that means this voltage is 0. I'm not applying any voltage here, no voltage coming. So EB junction is reverse bias. No bias means reverse bias. And I'm applying here an ICO. If ICO flowing, that means this junction is forward bias or reverse bias? This junction is
That
forward
is
bias.
also, so that is also reverse bias.
This is reverse bias. This is also reverse bias. So under this section, everything is reverse bias. So reverse bias, reverse bias. What is the reason? This reason is
Cutoff region.
Cutoff region.
You understand clearly what region means what? Whenever
Yes, sir.
I apply a negative voltage or 0 voltage, then current will not flow. Input current will not flow. Same time, I'm putting a reverse bias, only ICO is flowing. So this reason, when this kind of biasing is there on the transistor, it is said the transistor is working in the cutoff region. Okay. Now I go from here to here. Here is everything reverse bias, reverse bias. Now I go to this part, this section, and this section. This part. Here, IE is 0 or positive? IE, input current, is 0 or positive for this part?
That is positive for this part.
So this is the forward bias and reverse bias. So whenever VCB is positive, okay, then that is what reverse bias only. Okay, if you put NPN transistor NPN, okay, then your VCB become positive. Okay, here PNP, so VCB negative, but I am putting here, say this is a negative sign. Okay, so this is forward bias, reverse bias. So this region is called what?
Active region.
Active region.
Active region. So we always apply biasing according to this region. I have to make forward bias and reverse bias, and this section is called active region. Now, when my VE become, this is negative, and my VCB become positive. Here, suppose this is a positive, this is negative. It become opposite, then this become forward bias. Okay, this become forward bias, and this is already forward bias. So here, for this part, I is some value of IC coming, some value of IC coming, some value of IC coming. Okay, so this is forward bias, and this is also going in the opposite direction. This is the reverse bias, this is forward bias. So both are forward bias. So this region is called saturation
Region.
So saturation region means it is like a ohmic region. Saturation region का मतलब क्या है? Ohmic region. Saturation region is equal to ohmic region. And ohmic region का मतलब है you change the voltage, current will change. You go here from here, you are increasing the voltage, current is increasing. You are going from towards reverse bias, current is increasing. Okay, current is increasing like a ohm resistor, ohmic region. Now this is the part, this is the part, this is the part, this is part. Now tell me what is the resistance at in this section. If I plot my IV characteristics, IC versus VCB, this is my curve. Okay, what are the resistance for this curve? Tell me. What is the resistance for this curve? I versus B curve. This is a 0. What is this? Here you said na R is 0 for this curve. Now IV curve is like this. What is R for this curve? Tell me.
Sir, resistance is very high, sir.
Very high. If it is parallel, it is infinite. If it is a
Right.
parallel, so almost infinite. Generally, it is in mega ohm. Because now you're changing the voltage, but current is not increasing. Delta V upon delta I. You're changing the voltage, but there is no change in the current. Slope is almost parallel. Slope is 0. Slope is 0 means IV curve slope and delta IV, delta I by delta V slope is 0. Delta V, delta I is infinite. Okay, so this section, this part, when this kind of biasing is there, this is the reverse bias, this is the forward bias. At that time, current faces very high resistance. Output current faces very high resistance. Current is it's not increasing. It's changing the voltage also. So this section is called your active region. I told you na output current out here is resistance is low. This if I apply some voltage here now AC signal, this is a biasing. Now you have to apply some AC signal to amplify. So that AC signal will phase here little bit because once the biasing point is fixed, now if I apply some AC signal, yesterday we discussed, this point will shift. So AC signal here will face very less resistance. But the same AC signal when we measure here, we measure here, that will face very high resistance. So because of AC signal, whatever current is coming here, the same current will come here. But this time this current will face very high resistance. So that means there will be voltage gain. That is the basic principle of amplification. Okay. So this is common base configuration. So what are the takeaway points for discussion? You have to take VB equal to 0.7. That's it. You remember. And second thing you have to remember, this is the active region. This is the saturation region. This is the cutoff region. Reverse bias, the cutoff region. The forward bias, saturation region. Forward bias, reverse bias is the active region. These three things you have to remember. And now all these things I am going to discuss for common ammeter configuration. Common ammeter configuration, why? Because in this configuration there is a no current gain. Current is almost same. Okay, CP junction, no current gain. Only there is a voltage gain because there is a change in resistance. So that is the feature of common base. So common base may, as I written in the beginning, no current gain. There is a no current gain. There is only voltage gain. Okay, output resistance is mega ohm. Output resistance, input resistance Ri, a few ohms. Output resistance Ri, very high. Say mega ohm values. I will tell you later. It's around 500 mega ohm. Mega ohm very high. So current gain is not there. Voltage gain is there. Power gain is there. This is the feature of common base configuration. Now let me discuss that. Is time is there? No. Okay. I'll discuss now. Now. Do you want a break? Do you want to break?
Yes, sir.
Okay, 5-minute break. So we'll come back on 7:15.
सर आपका माइक म्यूट है।
Okay, because that is only useful for us. NPN and common ammeter. Okay, so this is NPN transistor. Now when I say common ammeter, this is my ammeter, this is my base, and this is my collector. Okay, so this is EB junction, which we have to make sure always forward bias, and this is my CB junction, which I have to make sure always reverse bias for this one. Okay, so here to here the voltage drop is VCB. Okay, and from here to here the voltage drop is now VBE. Ammeter is grounded. So this is your EB junction and this is your CB junction. Always keep in mind what is EB junction and what is CB junction. And I can also measure the voltage here, which is called VCE. VCE. So this VCE will be equal to what? VCE is equal to basically this voltage between here VCB plus VBE. VCB plus VBE. Always remember. Okay. Now I want to make this junction forward bias. If I want to make this junction forward bias, this is my base. Base is coming. So say base has a resistance, say resistance is RB here. And now I want to connect a battery here. So P should be connected to the P. And N should be connected to the N. So this junction become forward bias because the battery is common ammeter. I am putting the battery is VE. And now this is my N and I want to make CB junction. CB junction should be reverse bias. Okay. So N should be connected to what? Tell me, this N should be connected. Now say here resistance is say RC, some resistance RC, and I want to connect this N. N will go to plus or minus?
Plus.
Plus, minus. This is also plus, this is also plus. But in order to make this CB junction, this plus should be higher than this plus. That you don't make sure, okay? Because once you connect this PN, so automatically this become reverse bias. Automatically this become a reverse bias. Okay, this is also positive. And now here also positive. And I want to make this junction reverse bias. That means this plus should be higher than this plus, then only it is reverse bias. If here is 1 volt, it should be 5 volt. So this junction will become reverse bias. Okay, so that we'll see later. Now this is your VCC. Okay, and because here and here the voltage drop is VCE. Okay, now first thing is input characteristics. Here, if you want, you can put a resistance RE, but it doesn't require to understand RE. So first is input characteristics. Okay, if I will change the here this one VEE, okay, what will become? This voltage will here voltage will change VB and the current will change. Now NPN transistor, okay, NPN transistor. IE, if I apply forward bias, apply negative here, this will push the this will push the electron in this side. So hole will come in this side. So conventional current direction will be like this. IE will be here. Okay. Similarly, IC will be in this direction, and IB will so IE this one, IC this one. That means IB will be inside. This current direction is opposite. Earlier, IE was coming here, IC was here, IB was down. Now for NPN transistor, IE will go here, IC will also go here, and IB will go inside. Okay, so here IB will go inside. Is this point clear to everyone? भैया जो भी चीज क्लियर नहीं हो पूछ लिया करो. एटलीस्ट एक स्टोरी पूरी दिमाग में होनी चाहिए. सवाल तो आसान होते हैं, सवाल तो करना, तो जो सॉल्व करना है दैट इज वेरी डिफरेंट थिंग. ओके, बट some story should go in your mind. Okay, correct a story, then only you will feel what you are doing. Okay, and problems. So now this is here, my input current is IB. Input current is IB. Okay, and output current is same IC. I'm measuring here voltage now. I'm measuring voltage like this, output voltage, but this is opposite. So there's a phase change. If your input is like this,
ये मतलब VEE का पोलरिटी मुझे समझ में नहीं आ रहा है. वो NPN में तो ये तो फॉरवर्ड बायस है क्या?
ये तो फॉरवर्ड बायस तो है. ये तो
हाँ,
EB जंक्शन को हमेशा फॉरवर्ड बायस करना है ना.
हाँ, तो ये पोलरिटी N के साइड में जो पोलरिटी है वो नेगेटिव होना चाहिए ना?
हाँ, नेगेटिव है ना. नेगेटिव, ये प्लस है तो नेगेटिव ही है, ग्राउंड ही है.
ओके. एक्चुअली 4 to 1 दिखाई नहीं दे रहा.
हाँ, ठीक. तो ये ग्राउंड है, ये बड़ा करते हैं मैंने समझाने के लिए. ठीक है, तो इनपुट करंट इज IB एंड input voltage is again same, VB. Input voltage is VB and output voltage this time we'll say VCE. We'll say output voltage VCE. Output voltage, because VCE is a measure of VCB. VB is constant. Okay, so output voltage is VCE. Now input characteristics means IB versus VB keeping VCE constant, that is called input characteristics. And those input characteristics are what? That input characteristics is like this. It will come like this. IB versus VB. Here some loss around 0.7 volt. Keeping VCE constant, say this is 1 volt. So input characteristic is same. Forward bias का characteristic हमेशा ऐसे आएगा. IB का, अभी IB forward bias है, current IB है, input current. So this is your input characteristic. Nothing to discuss here. This resistance is very low. Okay. Now let me discuss output characteristics. If you want to ask anything here?
Sir, if we change the VCE, what will be the input characteristics?
You won't get any current. Because you are getting this IC because of only you're capturing na. If you stop pushing, you apply opposite force. Just now we have seen in the output characteristic, if you change the VC, current becomes zero na. Current will go down to zero. I'll show you here. If you not apply VC, what will happen? I'll tell you now.
Okay, sir.
So this is input characteristics. And the output characteristics now. Output characteristics. See, even though if you don't apply VC, but you are measuring IB versus VE curve, na? That will not affect. In this section, you will always get this current. Only IC you cannot get, because you are not collecting those things. If you apply reverse bias, some current will come, but if you apply reverse bias, this will become zero. Okay, so now let us discuss first what is VC, output characteristics here. So say output characteristics, basically output current is IC. Output current is IC. Okay, output voltage is here VCE. Okay, see, output can be anything, but the junction is should be reverse bias, this should be forward bias. That is a different thing. दोनों को mix मत करना है कि यहाँ पे VC क्या वहाँ पे VC भी था. In that case, VCB was the output voltage and VCE was the junction also. Here I am measuring VCE, but this junction should be forward bias, this should be reverse bias. They are two different stories. Don't miss that. Okay.
So
Now,
output is determined this which end is grounded, right?
Yeah, output where we are measuring here. Say this is here we are measuring output. Na? That will be given in the question. Where you want to measure the output. So for here, suppose here I want to measure the output. Okay. So I will take VC my output, and this is my junctions are different thing. For biasing different thing, where I am taking input, where I am taking output, that is entirely different thing. So I am giving input here. My signal I am giving here, I am measuring here, signal here. Okay. So this is my output current, this is my output voltage, and now input current is what? Tell me input current. What is the input current in this case? Input current
IB.
is IB. Okay. So now the IC versus VC curve, keeping IB constant, is called your output characteristics. Output characteristics. Now let me discuss this in detail. You can take output here also, put resistance here, you can take output here also. That is different thing. Okay, where we are seeing how much just current is getting increased or resistance, you have to see that terminal resistance higher or not. Okay, now let us say just now I have written one equation. My IE was, now I am doing common ammeter configuration. IE was what? IE what? 1 minus IE was alpha IE plus, tell me, it was ICEO. Okay. Now this was output current, this was input current. Now here input current become IB. So I want to change this equation for IB. So what I can write? I can write IC. This alpha. Alpha is what? Now first let me discuss what is alpha. Alpha is what? Alpha is basically IC minus ICO divided by IE. Okay. So this is current gain. Alpha is current gain in common base configuration. Alpha is current gain is common base configuration, and this is value is almost equal to 1, or you say less than equal to 1, or almost equal to 1. Okay.
So is
No.
it common emitter configuration or common base configuration?
Common base. Alpha is in common base. Okay. Common emitter we'll discuss. So this is the current gain in common base configuration. Now you know ICO is very negligible. ICO is microampere. ICO is very less compared to IC. So I can directly write my alpha is generally we say IC upon IB. Okay, this is in common base configuration, current gain. Now this equation I want to modify for common ammeter. This was common base. Okay.
So this is IB or IE?
Sir, that will be IE, I think.
This is
Last.
Alpha equal.
I. Here still we didn't discuss for IB, IE. Okay. So this is current gain. Okay. Now, because this is IC, IE almost same, so this is almost equal to 1. Now I can write this equation in some other way. I can write IC here, I can write IE here, I can write here IC plus IB. Because I know third equation, IC plus IB, and I will keep this ICBO. This was ICBO, na? ICBO. Correct this one. ICO we write now. This is ICBO. And now what will become now? You can write, you can take IC that side, So IC 1 minus alpha equal to alpha IB plus ICBO, reverse saturation current in the common base. And now IC I can write alpha upon 1 minus alpha IB plus ICBO upon 1 minus alpha. And now I define one more current again, alpha upon 1 minus alpha as a beta plus this I write now reverse saturation current in the common ammeter configuration. This is the equation for your common C base, common ammeter configuration. So IC is what? IC is beta IB plus ICO. Whatever current is coming here, that current will get multiplied here with beta. They'll form IC plus there is a reverse saturation current due to the reverse bias. Now beta value is very high. Okay. So beta is what? Now if I define beta in this equation, beta become what? Beta become, tell me what is beta? IC minus ICO. Okay, divide by IB. And now because ICO is very small, I can say my beta is, this is the exact formula, exact if it is given. Otherwise, you can write approximately IC is almost equal to IB. Now IB is very less compared to IC, so beta value become very high. So beta value generally you can take between 50 to 500. It may be more or less also, but generally you take beta value from 50 to 500 because this is in milliampere, this is in a microampere. And beta is called what? Beta is called current gain. Beta is what? Current gain in common ammeter configuration. Common ammeter configuration. Is there any question here? So here in this configuration, there is a very high, there is a current gain also. And we'll see resistance voltage gain also. Current gain you can see input current is IB, output current is IC. So current gain is obvious. And now we have to see how voltage gain also present in this common ammeter configuration. I'm erasing this one. Okay. Now let us discuss output characteristics. So common ammeter configuration means there is a current gain as well as voltage gain. Now let me draw the output characteristics. Output characteristic is IC versus VCE. Okay. Now suppose if my IB is 0, then and the here is the gain is beta. If IB is 0, then what is the value of IC? Tell me.
That is also 0.
So just now you written IC is equal to what? Beta IB plus ICO. If IB 0, then IC value is कितना होगा बताओ भाई? Beta is ICO. Beta 0, then IC will ICO. So if you are changing, because if you're changing the VCE, okay, then you are making this junction reverse bias. So at least reverse bias current is flowing in this resistance. Okay, because this curve is what? This curve is basically VCE. So this junction is reverse bias. So some current is flowing. Some current is flowing. This reverse saturation current at least flowing. If this is not IB is not coming, so at least reverse saturation current is flowing. Okay, so my IC will be equal to ICO. So ICO. Beta value says 100. Say beta value is 100. Okay. Here IB is 0 milliampere. Okay. Now I say my IB is, I'm changing this voltage and making some IB value. IB is, say, IB I'm keeping fixed. Say this curve is for IB. IB is 100 microampere. Then IC will be how much? Tell me. What will be the value of IC? If it is 100 microampere, beta is 100. IC will be IC is what? IC is beta 100. IB is 100 microampere. This you neglect. This become how much? 100, how much? 10 raised to power 4 microampere. Okay. Or 10 into 10 raised to power 3, 10 raised to power 10 by 3, at least 10 milliampere. Yes or no?
Yes, sir.
So my IC will be 10 milliampere. Or if I say this is a 10 microampere, if I say this is 10 microampere, then this will be at least 1 milliampere. Now I am again changing the voltage. I am making it IB, I am making it 20 microampere. Okay. Then this IC will become 2 milliampere. Now I'm making this IB equals to, say, 30 microampere, and this become now my 3 milliampere. So this type of graph you'll get if you plot the output characteristics. Now let me discuss. Now this reason, if VC is positive, tell me VC is positive, then this junction is reverse bias. Okay. And if IB is not flowing, that this junction is reverse bias. This region is cutoff region. This region is cutoff region. Reverse bias. How do you know reverse bias? Because IB is not flowing. That means your emitter base junction is not giving any current. If EB junction is reverse bias. And this is VC positive means VCB positive, because VCE what? VCE is equal to VBE plus VCB. Now VCE positive means now VB is 0.7. And now if VCE is greater than 0.7 volt, then obviously VCB will come positive. Understand this thing. Your VBE is 0.7 volt. If VCE is greater than 0.7 volt, my VCB is positive. VCB is positive means my N is connected to the plus and my B is connected to the minus. This is positive. So this is reverse bias. So in this section, this is, so say this is my 0.7 value. So this is 0.7 value of VCE. Now in this section, both junction IB is flowing. This is the greater than 0.7 value. So this junction is active region. This junction is an active region. Now what happens when you go below 0.7 value? If VC become less than 0.7 volt, if this is the, you have to see what is the value of this one in the question. So this is 0.7. If you are assuming 0.7, if VC become less than 0.7 volt, that time VCB will become negative. So this junction will become forward bias. So in this region, close to zero, when VC is close to 0 or less than 0.7 volt, okay, in that case, what will become? Either VC negative cannot go here. Okay, VB is positive. So either VC, if you want to put negative, then automatically it is forward bias. So if it is negative or less than 0.5, it is close to 0, that time both junctions are forward bias, then this is called your saturation region. Now take away point. For NPN transistor, your VCB value should be positive. NPN transistor VCB should be positive, PNP transistor VCB should be negative. Okay. And now some biasing is, if some biasing is given to me, by knowing the values, this values, I can immediately tell that my transistor is working, whether it's a cutoff region or whether it is working in a active region or whether it is working in a saturation region. By knowing these values, I can immediately conclude okay, how much current is flowing here. Okay. Before that, I want to tell you one more thing here. If VC becomes 0, okay, shall I erase this one? Tell me, can I erase this
Yes,
one?
sir.
Now you have this curve, okay, IC versus VC, okay, you have this curve, okay. And now if I go in this output loop, I can say minus VCC plus ICRC plus VCE equals to 0. So my VC is what? My VC is VCC minus ICRC. Yes or no? In output loop. If I go in this loop, this is my minus VCC plus ICRC and then plus VC. Let me plot. This is in different way. Say I have a common ammeter configuration. Okay. Say here the resistance is RC. I'm applying NPN transistor, so VC should be positive, N2 plus, and this is my ammeter, this is my collector, this is my base, and here some resistance is a RB, say some resistance is a VB positive, NPN positive. So this is my biasing, okay. And now I'm writing, this is my VCC, this is my VCE, and now applying KVL. Here IC NPN transistor, IC is flowing inside, okay. IB is also flowing inside, and IC plus IB combined giving you the current IE. Okay. Now let us discuss these things. Now here VC is equal to VCC minus RC. Okay. If VC becomes 0, now this is the equation of line. If I draw this equation, this is equation of line, yes or no? Tell me. If I write the IC RC will be what? This will be VCC minus VCE, and if I want IC, that will become VCC upon RC minus VC upon RC. Is this the equation of line or not?
Yes, sir.
Yes, okay. So this is the equation of line. Okay, this is y equal to mx plus c and mx plus c. Now if I put here VC 0, my IC will become what? VCC upon RC. In this section, VC is 0. If I put VC is 0, are you can you see this one right here? So your equation is basically IC equal to from here, IC equal to VCC RC minus VC upon RC. This is equation, and this is called load line equation. Load line equation. Now if I put a VC equals to 0 here, my IC will be VCC upon RC. This IC is called IC saturation. This is called IC saturation. And if I put IC equal to 0 here, then my VC will be equal to VCC. So this VC will be equal to VCC. Now I will tell you the easiest way to find any circuit in which operation region this is working. The question may exam what they ask. This is the circuit, tell me whether it is working in the active region, cutoff region, saturation region. That is the final conclusion we have to tell. We have to see the biasing and we have to tell. I will tell you the easiest method to find the what is the operation region for any transistor. Okay. Now you know, understand this curve. You know the load line. So this is the maximum current can flow in the circuit. If this is the maximum current can flow in the circuit, okay. Now if you solving this circuit, you measure the IC. What is IC flowing in the circuit? If this IC is less than, if this IC is, your IC is coming greater than IC saturation. If your IC is coming greater than IC saturation value, then you can say the operation region is saturation region. The operation region is a saturation region. Why? Because you are near almost VC become less than 0.7 volt. You have become here, you come here, or you're going negative. Because IC can go up to here is maximum. If your IC is greater than this one, that means you're going in this region. So without measuring VCB value, okay, VCB value will tell you whether it is a active region or region. Without measuring the VCB residue value, you just measure IC in the circuit. If IC is greater than IC saturation is coming, then you can safely say then it is working in your saturation region. Okay, if IC comes less than IC saturation, then you can say the operation region is cutoff region. Operation region is your active region. Operation region is your active region. Okay, and if IC is 0, IC is 0 or equal to ICEO, then you say my operation region is cutoff region. So by knowing these things, you can immediately tell what is the reason, and we will show you in the detail how this is correct. Okay, let me take an example now in problem, and then you understand what is the meaning of this one. Can I erase this one?
Yes, sir.
Okay, now understand everything with example, then it will be clear to you. Say I have a resistance. This is 200 kilo ohm. This is the 5-volt battery. NPN transistor. So NPN current will go always from P to N. So NPN transistor means like this. And now you have a resistance here. And you are applying voltage here. This is 10 volt, okay. And this is 3 kilo ohm. And now you have to find the operation region. Question is, find the operation region and operating point. Okay. So this circuit has, and now it says beta value is given to you 100. In the question, beta value is 100 and VB is 0.7 volt. It is given. So here to here voltage drop is VBE. Okay. Say this is RC, say this is RB, say this is VCC, and say this is VBB. Okay, I don't need to name. Now we have two loops here. IE is coming here, NPN transistor, IB is flowing like this, and IC is coming like this. So this is the input loop and this is my output loop. Now write the equation first for input loop. Okay, this is -5 plus IBRB plus IBRB, okay, plus VBE equals to 0 in this curve. -5 plus IBRB plus VB is 0, and from here I can find the IB value. IB value is what? IB value will be 5 minus 0.7 volt, VB is 0.7 divided by RB. RB value is 200 kilo ohm. Tell me what is IB is coming? Tell me IB value.
2.5 milliampere.
Milliampere or microampere?
Sir, microampere.
21.5 microampere, na? How much? It is coming value?
Yes, sir.
2.15. Yes, sir.
ये आना चाहिए. B, this is 10 raised to power 5. Okay, and this is how much? This is 4.3. So it's correct only. Microampere, this is 21.5. So what is the value of IC now? IC will be always beta IB, almost. Okay, beta is 100, IB is 21.5 microampere. So this become 2.15 milliampere. Tell me yes or no.
Yes, sir.
Yes, sir.
Okay. Now I want to find the operation region. I told you simplest method. Always first find IB, multiply with beta, and you find the IC. Now you calculate IC saturation. Now, what is the, I will use this one, huh? Find the value of IC saturation for this given circuit. IC saturation, always make VCE 0. So if I make VCE 0, because my curve was like this, IC saturation was here. For VCE 0, for VCE 0, IC become IC saturation. And what is the formula for IC saturation? Tell me. What is the formula for IC saturation? What is the equation in this output loop?
VCC by R.
ICC equal to
VCC by RL.
VCC by RC. Very good. Because the equation is what? Equation is VC equals to VCC minus ICRC. To make VC 0, so IC saturation will become VCC upon RC. Tell me what is the value of IC saturation? So VCC is your 10 volt, RC is your 3 kilo ohm. So this become 3.3 milliampere, which is, so IC saturation is greater than your measured IC. So whenever this situation occurs, your operation region will be active. Because why? Why? Because this is IC saturation and your current is not here. Your current is somewhere here. Here. Somewhere here. So you are in this region, not here. Okay, we'll discuss this thing more in detail. Now the operation region is active. Now how to verify that the operation region is active? Let us calculate. So this is the maximum current will flow. So actual current is this one, and this is less than. Now this is my current VCE. Let us find now VCE. Now go to the output loop. This was input loop. Now go to the output loop. Output loop. Output loop says VCE is equal to VCC minus ICRC. VCC is your 10 volt. IC is your 2.15 milliampere. And RC is your 3 kilo ohm. What is the value? Tell me. Solving what you'll get. VC equal to 3.55 volt. Tell me it is correct or not.
Yes, sir.
Correct, sir.
Now VCE is equal to VCB plus VB. Yes or no?
Yes, sir.
So what is the value of VCB now? VCB will be VCE minus VBE. This is 3.55. VB is 0.7. How much is coming? Tell me. VCB. What is the value of VCB?
2.85 volt.
2.85 volt. Okay. And this is the positive or negative?
Positive one.
Positive. And this VCB should be for what? Positive for reverse bias? Because this is the NPN. This N should be connected to the plus. So what is the definition of biasing? This should be forward bias. This is already forward bias because some IB is flowing. If IB is 0, then this is also reverse bias. This is a forward bias. And output junction, CB junction, VCB is positive. If it's a PNP transistor, VCB should come negative. In common ammeter configuration, so VCB is coming positive. That means you have working in the active region. So this shows reverse bias. And IB value shows coming. That means shows IC is flowing. That means it is a forward bias. Okay. IC value is 2.1 milliampere. IC value is 2.15 milliampere, which is greater than ICO. ICO is not given in the question. So, but this is milliampere, this is microampere. So this is also, it shows input junction is forward bias. This shows input function is reverse bias. Forward bias, reverse bias is active region. And now you can understand this in a way. Now you can plot the graph. This is IC, your VC, this is your graph. Okay, and this is your load line. This is IC saturation. And now what is your operating point? Your operating point is VCE into IC is your operating point. Where your transistor is working in this graph. So VC is your 3.55, IC is 2.15 milliampere. IC saturation is how much? 3.3 milliampere. So basically your operating point should be on some curve. What is the value of IB? 21 point. So suppose this curve has a
21.5 microampere.
So suppose this curve and this curve has 21 ampere. So your point is here somewhere on this where the current is here, and the corresponding this value is 3.55 volt, and here the current value is 2.15 milliampere, and this point is far away from zero. That means this point is corresponding to the active region. For active region, this value should be greater than 0.7 volt. This value is should be greater than 0.7 volt. So whenever you solve a circuit, if your VC is coming less than 0.7 volt or close to 0 volt, you always should have doubt in your mind whether my transistor is going in the saturation region. If it is above 0.7 volt, or you for safety, if you solve the circuit, if VC is greater than 1 volt, you can surely say that it is in the forward bias region. Okay, if VC is greater than 1 volt, then if your VB is given 0, then anything positive value of VC will give you positive VCB, because VC is equal to VCB plus VB. If in the question VB is given 0, then VC is equal to VCB. If VC is positive, VCB positive. But always question VB will be given 0.7. So then, for make sure whether your active region, your VC value should be greater than 0.7 or at least greater than 1 volt. Then you can make sure that is you are in active region. And easier than this one is just to find the IC saturation value. You find the IC and IC saturation, compare that one. If IC is less than IC saturation, you are in the active region. That is a confirm check. If IC becomes greater than IC saturation, then it is a confirm check that you are in the saturation region. And now tomorrow we'll solve more problem. So now things become very easy. You will be given different type of circuits, and you have to tell what is the active region. So you will always first you will find the IB, and beta will be given. You will find the IC. You will calculate IC saturation. You compare those things, and you will say whether the operation region is active or saturation. And if it is a cutoff, that will also those circuit also we will discuss tomorrow. Okay. So I'll stop here. Thank you. Is there any question to any student? You can ask, and if any doubt is there. Otherwise, tomorrow we'll solve the problems, and then more clarity will come. Karishma, is clear?
Yes, sir.
Okay. Deepak,
Clear, sir.
Amarpreet.
Clear, sir.
Okay, thank you. Chalo.